Good morning, good afternoon, good evening, class. This is Mr. Arosena, and today we're going to talk about related rates. Related rates are when we sometimes have to describe a quantity. We'll call it quantity A, and quantity A depends on the rate of change of another quantity. We'll call quantity B. This actually happens quite a lot. There's lots of things that depend on the rate of change of something else. Now, we can describe, using some math, which we'll do today with a bunch of examples, we can describe the rate of change of A in terms of the rate of change of B. And that's really what a related rate is. We're relating the rate of change of A with the rate of change of B. Okay? And we'll illustrate this. It's easiest to illustrate this with just a lot of worked out through examples. And the process is the same for almost all the examples we work through. Okay, so for example, here. Air is being pumped into a spherical balloon, so its volume increases at a rate of 100 cubic centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Right. Well, let's discuss what information we're given. So we have rate of fill. So the balloon is being filled at a rate of 100 cubic centimeters per second, and it's spherical. So let's draw a circle. There's my spherical balloon. Oops. And to make it sure it's kind of spherical, we kind of draw like, stylize it a little bit. So spherical. Because I have a spherical balloon, and we want to know what is the rate of change of its volume when the radius is equal to 50 centimeters. Okay? So, now, as we've been discussing all throughout this chapter, a rate of change is really just a slope, and a slope is really just a derivative. So in effect, the question is really asking us, what is the rate of change of volume, or in other words, what is the value of the derivative of the volume with respect to time, because it's a rate. Well, in order to figure this out, we first ask ourselves, what is the volume of a sphere? Well, volume of a sphere is 4/3 times pi r cubed. And that's really all we have. This is the information that relates the volume to this radius. Okay, so the question is in effect asking us, what is the rate of change of the radius? And rate of change is really just a derivative, because a rate of change is a slope, and as we've discussed earlier in this chapter, a slope is really just a derivative. So the rate of change of the radius is really dr dt. And what is that equal to? Right. This 100 cubic centimeters per second, this is actually going to be the change of volume. So this quantity here, this is my change in volume. Or in other words, the derivative of the volume. So how do I relate the derivative of volume with the derivative of radius? Well, we can do the following. The formula that governs volume for a sphere is as follows. 4/3 pi r cubed. Okay. This is the equation that relates volume to radius. And since we want to find the derivative of the radius, let's just take the derivative of everything with respect to time. So d by dt, and we'll take this d by dt. And it'll give us the following. Derivative of volume is just dv dt. Derivative of the radius with respect to time is going to be 4/3 pi. Derivative of r cubed will be 3r squared, and then we have a dr dt. Right, after some simplification, we get the following. We'll bring all of this over to the other side, because we really want to get dr. We want to get this by itself. So we'll get, see, the 3's will cancel out. So we get the following. dv dt divided by 4 pi r squared is equal to dr dt. Or if I clean it up a little bit so it looks a little nicer, we'll get dr dt is equal to 1/4 pi r squared times dv dt. Now we can fill in some numbers because we have a lot of numbers already. dr dt's are unknown quantity. We know our radius because the problem tells us they're at 50 centimeters. That's my radius. And we know that the rate of the volume is being filled at a rate of 100 cubic centimeters per second. Centimeters cubic per second. So radius will then be increasing as follows. Let's see, so 1 times 100, this will be 100, divided by 4 times 50 squared is, I believe, 1,000. 50 squared is 200, or 2,500, oh, but 10,000. 1 over 10,000 pi. Those will cancel out, so the radius is increasing at a rate of 1 over 10 pi centimeters per second. And we can calculate this out so we can have an approximate answer, but leaving it as 1 over 10 pi makes more mathematicians happy. Alright, so that's example 1. Alright, let's go to a second example. In the second example, we have an 8-foot ladder resting on a vertical wall. Bottom of the ladder slides away from the wall at a rate of 1 foot per second. How fast is the top of the ladder sliding down and the bottom is 6 feet from the wall? So in this situation, this is what the picture looks like. We have a wall. We're going to assume it's at a right angle to the ground as follows. And then we've got a ladder like that. There we go. Okay, the bottom of the ladder, I think, yeah, bottom of the ladder is sliding away at 1 foot per second going this way. So that's going 1 foot per second. And the actual ladder is how fast is the top ladder sliding down, and the bottom is 6 feet from the wall. So this is going to be 6 feet. Yes, and this is an 8-foot tall ladder. Right, and we want to know how fast is this going down. Okay. Well, I'm going to assign some variables to this. We'll call this x and we'll call this y, simply because it's easiest that way. And we'll kind of look at our picture that I've drawn. What kind of relationship does x, y, and this 8 have? Well, as you can see, this is a right triangle. We're assuming it's a right triangle because the wall we're going to assume is at a right angle to the floor. So we can probably use Pythagorean theorem to help us solve this. A squared plus b squared is equals c squared. Or in other words, for this particular case, it'll be x squared plus y squared equals 8 squared, which is 64. Okay. And ultimately, we want to know how fast is this point sliding down. And how fast it's sliding down is really a rate, which is really a derivative. So ultimately, we want to know what is dy dt. This 1 foot per second is dx dt. So let's take the derivative of everything. So I'm going to take the derivative of this with respect to time, take the derivative of this with respect to time, and take the derivative of this with respect to time. This one becomes derivative of x squared is 2x dx dt. This is going to be 2y dy dt. And derivative of 64 is just going to be 0. Hooray, that's easy. Now, we're going to get dy dt by itself, because ultimately that's what we're interested in. So dy dt is going to be negative 2x dx dt, and then divided by 2y, or simplified, this is going to be x over y, negative x over y, dx dt. Right. We can almost fill in the numbers. The only thing we need to know is what is y. We need to know what this is. And to figure that out, we can use Pythagoras Theorem, because Pythagoras Theorem holds true. We know this is 8 feet. We know x is 6 feet from the wall. So as an aside, we'll do this Pythagoras Theorem calculation of 6 squared plus y squared equals 64. So y squared is equal to 64 minus 36. Y is going to equal the square root of 18. Right? No, square root of sorry, 28. Alright, now we can fill in the rest of this. We can finish solving the rest of this. So dy dt is going to equal x, which is, or negative x, which is 6, times dx dt, which is 1 foot per second, all divided by the root of 28. So dy dt is really just negative 6 over root 28 feet per second. Now, as you can see from the last two examples, all we really did was figure out what equation what equation we were working with. In this case, we were working with Pythagoras. Take the derivative of that equation with respect to time, and then solve for the rate that we're interested in, which we identified based on this diagram that we drew. So a lot of the times in the related rate problems, the process is very similar. We figure out what the equation is, and then we just take the derivative of it with respect to time, isolate for the rate we're interested in, and then fill in the numbers that we know. Okay, so here's some tips when dealing with related rate type questions. Now first, from the problems, you want to identify what is actually being asked of you. So identify what's being asked, and then identify what are the known quantities that are being given to you. Sometimes you have to calculate the known quantities. Like for example, in the last example we did, you had to calculate what the value of y was based on what x and the hypotenuse was. So keep that in mind, that sometimes you have to calculate some of the values in order to actually go ahead and solve the question. Now, if you're not entirely sure what equation is being used to solve the question, or solve the problem, draw a diagram. Drawing a picture will help you visualize what's going on, and it'll probably help you determine what equations are going to be useful in solving the particular question. Okay. And lastly, as part of the process, you want to differentiate both sides with respect to time. Okay. Or take the derivative of everything and then make it d by dt. Okay. So those are some of the tips that I've got for you. Alright, if you have any questions, come see me in class. And here is the assignment for this particular section.